Welcome back. This is lesson 4 of machine learning Zoomcamp session 1, and we'll talk about linear algebra now. So we'll talk about simple operations of linear algebra, like vector operations. We'll talk about multiplication, and we talk about a special operation called matrix inverse. So we'll start with a simple vector operation, which is multiplication. So if we want to multiply a vector by some number, so let's say we want to multiply a vector by number 2, what we do is we multiply every element of this vector by 2. So in this case, it's 4, 8, 10, 12. And you see that the way I write vector is it's like a column. So it's a column vector. And this is just a notation. This is how things are usually written in linear algebra. So in linear algebra, typically the vectors are columns, not rows. If you remember the way we did it in NumPy, so let me just quickly show you. So in NumPy, actually the vectors are rows. So here we have it as a row, not as a column. So this is just a convention. So this is just how things are written usually in linear algebra. So they are columns. And if we want to add two vectors, let's say this is vector u, this is vector v. So what we do is, and if we want to add two vectors, what we do is we add each element of a vector, and the result is so 3, 4, 5, 7. So this is pretty much the same as we saw in the previous lecture in NumPy. So we just add things element-wise. So if you see, so here I have these two vectors, u and v, and if we add u plus v, then we have element-wise addition. And yeah, here you remember from the previous lecture that we can multiply a NumPy array by 2, and then the result is multiplication element-wise. So this is basically the same happens in linear algebra. Now we'll talk a bit about more interesting things about how we can multiply vectors with vectors, and how we can multiply a matrix by a vector, and how we can multiply a matrix by a matrix. So let's start with vector-vector multiplication. So it's also called dot product, or sometimes inner product. So let's say we have two vectors, u and v, and we want to multiply vector u by vector v. And this is not element-wise multiplication like we do in NumPy. So remember, in NumPy, if we do this u times v, so we have an array where we multiply elements element-wise. We have element-wise multiplication. So actually in linear algebra, this dot product produces a number. So the way we compute it is we multiply again each number separately, like for element for the first element of u, we multiply it with the first element of v. For second element of u, we multiply it with second element of v, and so on. And what we get is 2 times 1. So here we have 4 times 0, 5 times 0, 6 times 2. And then what we do, we sum the results. And what we have as a result is we have 2 plus 12 here, and the result is 14. So basically, the formula, if we want to write the formula, so we have a sum that goes over all elements of our vectors, right? So let's say it goes from 1 till n, where n is dimension of the vector, and then we just multiply if element of u with the if element of v. And this is the result of a dot product. So we just saw it. However, the way we usually write it in linear algebra is maybe it's a bit counterintuitive at first. So the way we do it is, so this is, remember, so this is u, which is a column vector, but this is v, which is a row vector. And if we want to turn a column vector into a row vector, we use a transpose operation. So transpose operation turns columns into rows. And so this is just a notation. So if we want to, and you will see later when we multiply matrix with vectors, why it's the case. But this is just notation for dot product. So for multiplication, we will need to have a row vector and a column vector, and the result is a dot product. So this is how we usually write dot product. So this is a notation for dot product. And as we already saw, that the formula for computing the dot product is like this. So and E goes from first element to the last element. So this is the dot product. We can quickly implement it. So let's say, yeah, we want to write a function that does vector-vector multiplication. And then we have two vectors here, u and v. So first, what we need to do is make sure that these vectors have the same size. And we usually do this by checking the shape of the vectors. So if you remember, so let me just show you what shapes prints. Shape. So shape is the size of the array, right? And the first element of this tuple is 4, right? And then v should also have 4. And if they are different, then multiplication doesn't make sense. So we need to make sure that the vectors have the same size. So that's why we have this assertion here. And then, yeah, so basically what we do next is, again, in our formula, we have also n, which is the number of elements the vector have. So let's say we can write that n is this shape of u or shape of v, doesn't matter because they have the same shape. And we just go over a loop, go over all the elements here of the arrays. So we say, okay, we first need to have a result, the result variable, which contains our dot product, right? And then we say that the result should contain, so first of all, so we do this product between each element. So let me just draw the formula here. So the formula is ith element of u times ith element of v, right? And then we go from 1 to n. So actually, because we are in numpy arrays and numpy arrays are indexed from 0 to n minus 1, and then the size of the array is n. So instead of going from 1 to n, we go from 0 to n minus 1. And this is how we implement this, right? So we have this part here, which corresponds to the part inside the sum. And this for loop is actually the sum. And then what we need to do at the end is just return the result. So this is how we translate this formula into code. So now we can test it. Vector multiplication between u and v. So it should return 14. So yes, like we calculated. Actually, in NumPy, there is already a function that is doing this. It's called dot product. And this is how we use it. We just multiply vector u by a vector v, and the result is also 14. So this is how we translate this formula into code. So we talked about vector-vector multiplication. Now let's talk about matrix vector multiplication. So in matrix vector multiplication, so let's say we have this matrix U, that we want to multiply by a vector v. So this is capital and this is lowercase. So we want to actually compute u times v. So u is a matrix, v is a vector. And the way we do it is, so we take the first row of matrix u and multiply it with the vector v. So you see, this is a row, and we multiply it by v. So this is exactly like we have here. So we have a row vector and a column vector. And again, we have a row vector here. So this is, let's call it u0. So we will just use the same notation as in NumPy. So we'll start with 0. So u1, u first, and u second. Right. So what we need to do now to calculate the multiplication between matrix and a vector, for each row of the matrix, we multiply it with v. Okay, so this is how we do this. So we take the 0th row of u and multiply it with v. Then we take the first row of u and multiply it with v, and the second row and multiply it. Right. So this is the result. So basically, for each row, we do a matrix. For each row of u, we do a vector multiplication with v. So this is how we compute a matrix vector multiplication. So let me just write it once again. So let's say we have this vector u, matrix u, and then we have, let's say we have k elements of here. So from u0 to u k minus 1. So in total, there are k rows. And we want to multiply it with vector v. So this will be just vector v. And of course, dimensionality here should match. So this vector here and this vector here should be the same. So the, let's say dimensionality can be n. So both have n elements. And yeah, and the result is a dot product between each row of the matrix u and the vector v. So this is how we do it. Let's implement this in NumPy. So let's implement it in Python. So I already have the matrix u here. This is it. And let's implement matrix vector multiplication. So I have big capital U, and I use capital here to denote that this is a matrix. So first we need to make sure that dimensionality match. And if you remember, so here we have the shape field here, and we are interested in the number of columns. So remember here, if I go back, so the number of columns in U should match the number of elements in V. So the number of columns in U is basically the dimensionality of each row vector of U. Right? So if there are 4 columns, it means that the vector U0 has dimensionality of 4. It has 4 elements. So it means that the second dimension, the number of columns, should match the first dimension. So then we have the number of rows. We can use k, or maybe we just call it number of rows, which is u shape 0. So this is the dimensionality of our resulting vector. So this is the results. So because we have 3 rows, so there are 3 rows in matrix U. That's why we have 3 elements in the result of the multiplication. So this is our result matrix. Let's initialize it with zeros, and number of the dimensionality of this vector, the size of this array, is number of rows. So okay, and then we have a loop So we want now to go through each row of the matrix U. So we do this, so we have a loop. And now we need to access the ith row of U. This is what how we do this. And we need to calculate a dot product. So this is vector-vector multiplication between the ith row of U and the vector V. And actually we write the result as the ith element of the result. And then what we do at the end is we just return the result. So this is how we translate this formula into a Python code, right? So again, we create we create an empty array, and then for each element of the array, we compute the vector-vector multiplication between each row of U and the vector V. And so let's test it. Matrix vector multiplication. So we do it between U and V, and we get a one-dimensional array. So in our case, this is a vector. And again, in NumPy, if we want to use NumPy for that, of course, we don't want to write a function for computing this multiplication every time. We just use a function again, dot. So, and because we invoke this function on a two-dimensional array, NumPy knows how to actually multiply it, that it needs a dot product, and you see that the result is the same. Right. So this is how we do matrix vector multiplication. Now let's talk about matrix multiplication. Let's say we have a matrix U, which is a capital U, and we have a matrix V, capital V, and what we want to compute is multiplication between matrix U and matrix V. What we do here is we look at, so we take a matrix V and we break it down into multiple columns. So we have a column V0, V1, and V2. And we look at the entire matrix U as is. And the result of this multiplication is a new matrix where for each column, so it will have three columns. For each column, we have, so column first is a matrix U multiplied by vector V0. Then it's matrix U multiplied by vector V1 and matrix U multiplied by vector V2. We represent matrix multiplication as a bunch of matrix vector multiplications. So let's implement this. So we already have a matrix V here. So we will do matrix multiplication. So we have two matrices here, U and V. So what we need to check here is the same, so that here that actually this multiplication makes sense, that we can multiply a row of U with a column of V, right? So we need to make sure that the dimensions match. So we basically can use the same thing here. So this is the check that makes sure that the multiplication makes sense. And then we need to create a new matrix. So let's call it result. Again, we use initialize it with zeros. So the size of this matrix will be the number of rows of this matrix will come from here. When we multiply U by V, we will have a new vector that has dimensionality 3 because there are three numbers. So it will be 3. So UV will have 3 rows and it will have also 3 columns because there are 3 columns in V. So number of rows comes from U. So this is the number of rows of U, and number of columns comes from the number of columns of V. And then we create a matrix with results, which with number of rows coming from U and number of columns coming from V. And then we do a loop. So here we loop over the rows of V. So we first do it for V0, then V1, V1 and V second. So we do it over for each column. And then let's take U, the ith column of U, which is, we use this notation. So we take all the rows and ith column. So now we multiply this. So the result of multiplication will be matrix vector multiplication between, so sorry, it should be right? And then we multiply U by this ith column of V, right? And then we get some result, U VE. So this is the result of multiplication of our matrix U with vector V. And what we need to do now is put it to the result. So this is our matrix result. And it has, so let's say it's 3 by 3 matrix filled with zeros. Yeah, actually, these are 0 here. So what we want to do here is replace these zeros with some numbers. So we want to replace this with results of multiplication. So here it will be U times V first. And to reassign a column of a two-dimensional array, this is the syntax we use. So we say that for ith column of the result is this multiplication. Right? So we do this we repeat this for every column of V, and we return the result. And this is our multiplication. Then let's check it. So between U and V. And this is the result. And again, you probably figured out this pattern by now, is that if we want to do it with plain NumPy, if we want to multiply two matrices with plain NumPy, we use the dot method. And you see it returns the same result, right? So, which means that our matrix multiplication method works. And this way, we managed to express matrix multiplication using matrix vector multiplication. And then in turn, we expressed matrix vector multiplication with vector multiplication. There are still two topics we want to talk about. Let's talk about them. So first, I want to talk about the identity matrix. We call identity matrix as capital I. So this is the identity matrix. And the identity matrix is a square matrix where on the diagonal we have ones and we have zeros everywhere. When we take any matrix, let's say we have matrix U, and we multiply it by I, and of course, like dimensions should match here, we get U back. Or we can put it in front, and we can again get U. So identity matrix is like a number 1. So if we multiply number 1 by any number, we get the number back, right? And no matter on which side we have this one, we get the number back. So in principle, this is the same, right? So this is the same, but so this is like a number 1, but for matrices. If we need to create this identity matrix, so in NumPy, we use the function I don't know why it's called I, but here we just specify the dimension of the identity matrix. and it gives us a matrix where on the diagonal we have ones and we have zeros everywhere else. Yeah, and we can see, let's say if we create this identity matrix of size 3, then let's say we have B here, so we can test it, and we see that yeah, when we multiply V by I, we get the matrix V back. And here we have 3 columns, so that's why our I should be 3-dimensional. It should have like the size of 3, so it should be a 3 by 3 matrix. So why we are talking about this I matrix? It's useful for explaining what a matrix inverse is. So let's say we have a matrix A, and then the inverse of A, we usually call it A minus 1, is a matrix such that when we multiply it by A, we get I. To compute the inverse, so first of all, only square matrices have inverse. So square matrix is a matrix for which the number of rows equals to the number of columns. So actually we need to have a square matrix. So let's just take the first 3 rows of B. So this is our matrix, square matrix, and let's call it V square. Yes. This is our matrix. And to compute inverse of this matrix, we use a method from NumPy called inv. It lives in the linalg package, which stands for linear algebra, I assume. And so this is how we use it. And then the result is some matrix, which let's call it VS inv. So this is the inverse. This, and then again, let's print it. And when we multiply VS inverse, when we multiply these two matrices, what we get is an identity matrix. This will be quite useful for linear regression. We will see that in the next session. And for this lesson, that's all. And next, we will have our last lesson of this section. We will talk about pandas, which is a library for manipulating tabular data in Python.